Hi, everyone. We're finishing lesson 26 with discussing the chi-square distributions. These distributions will be used to find confidence intervals for standard deviation and variance later on. For confidence intervals for standard deviation and variance. And there's a key feature of these chi-square distributions which will be related to these parameters. So that's the Greek letter chi. If you go on a college campus, well, not now, but if you go on a college campus, maybe a year or two from now, then you may recognize this Greek letter chi on, say, a fraternity. Chi-square distributions. And these guys have, again, both similarities and differences compared to the z and t distributions. So, for example, what are some similarities that these chi-square distributions have with the z distribution, let's say? And again, the t distributions look a lot like this guy. All right, well, the chi-square distributions are continuous. I'll tell you right now that a more generic chi-square distribution looks like this. Okay, it looks a little bit stranger. And yes, there is a brick wall at 0. We'll get to that. Okay, but both chi-square distributions and z and t distributions are continuous. We have this density curve here, right? The total area under the curve is 1. That corresponds to total probability. And like for the t distributions, there are infinitely many chi-square distributions indexed by the number of degrees of freedom, or df. So in that sense, they're like the t's. But there are also differences. Before we get to the differences, let's talk more about degrees of freedom. All right. Again, different chi-square distributions corresponding to different numbers of degrees of freedom. The number of df can be any positive integer, 1, 2, 3, and so forth. Again, like for the t's, for most basic applications, if n is the sample size, then we typically want to use the chi-square distribution on n-1 degrees of freedom. So for example, if the sample size n is 10, then we want to use the chi-square distribution on 9 degrees of freedom. Okay, just like for a t distribution. And the z distribution did not have any degrees of freedom. So far, I've been talking about some similarities between the chi-square distribution, distributions, and the t distributions. And like for the t distributions, as the number of degrees of freedom increases, a chi-square distribution will look more like a normal distribution. Now, the t distributions look more and more like the z distribution, the standard normal distribution, as the number of df approaches infinity. But the chi-square distributions, as the number of df approaches infinity, approaches a normal distribution in general, but not a standard normal. It does approach a normal distribution. The curve looks more and more bell-shaped, but it won't be a standard normal. The mean will not be 0. In fact, in general, the number of degrees of freedom will be the mean for the chi-square distribution, and it's never 0. There's no such thing as a chi-square on 0 degrees of freedom. Right. And again, if the number of degrees of freedom is large, we might approximate a chi-square distribution by a normal distribution, although that's less frequent. It's more often that we approximate a t distribution by a z distribution if the number of df is huge. Okay, let's discuss some differences now between the chi-square distributions and the z and the t's. The brick wall I was talking about. When you look at a chi-square distribution and you draw a density curve, there is a brick wall at 0. A chi-square random variable can only take on non-negative real numbers as values. The value of a chi-square random variable cannot be negative. Of course, that was not true for z or t. For example, up here, let's look way back at the standard normal z distribution. Of course, you could get negative values for z, like negative z-scores. T-scores can be negative also. T-scores can be negative also. But chi-square values cannot be negative. Well, chi-square can never be negative in value, and you can probably tell that the mean cannot be 0. I mean, look at this thing. There's no way that the mean is at 0. We'd pretty much have to have negative values in addition to these positive values. We would need negative values to be legal pretty much. So the mean is not 0. And again, you won't have to really know this, but the mean of a chi-square distribution equals the number of degrees of freedom. Remember that the mean was 0 for the z and for the t's. Also, we lose a key property. We lose symmetry about the mean. The z and the t's, they were all symmetric about the mean. So see here, the z curve in black, the t curves in orange and blue, they're all symmetric about the mean line at 0. Chi-square distributions, they're not symmetric, they're asymmetric. So we lose some key properties. That's one reason, for example, why, remember how I mentioned before, we're going to use these distributions to do CIs, confidence intervals, for standard deviations and variances. These CIs will not be symmetric about their mean. And in part, that's because of the asymmetry of the chi-square distributions. Also, what else is true about standard deviations and variances? They're never what? In value. They're never negative. And that's also related to the fact that chi-square values are never negative. We have nothing over here. So what do some of these look like? Actually, the chi-square density curves on 1 and 2 degrees of freedom, they look a bit different. They look like slides. So in red, here's the chi-square density curve on 1 degree of freedom. And in blue, here's a chi-square density curve on 2 degrees of freedom. These are like slides. They're a bit unusual because other chi-square curves have a peak that's not on the y-axis. They have a peak that's a bit over to the right. So for example, in orange, here's the curve for a chi-square distribution on 3 degrees of freedom. Okay. Again, you cannot take on negative values. These guys are out. And the curve peaks a bit to the right of 0. Then it falls off. In blue, this dotted blue curve, that's for the chi distribution on 5 degrees of freedom. And in gray, you see the chi-square distribution on 10 degrees of freedom. You may be able to see that as the number of degrees of freedom increases, we're approaching more of a normal bell shape. But the mean cannot be at 0. In fact, the mean for a chi-square distribution is always at the number of degrees of freedom. So for example, if you have a chi-square distribution on 1,000 degrees of freedom, then the density curve will look almost normal bell-shaped. It'll look very close, and the mean will be 1,000, the number of degrees of freedom. So again, the chi-square distributions look a lot different from the z and the t's, and we're going to use these to develop confidence intervals for standard deviation and variance. Okay, so what values from these distributions are we going to use to construct our confidence intervals? They're called critical values. And that's going to be the topic of lesson 27.